Professor Chen is a great expert on string theory, gravity theory, and ADS course. So the title of his lecture is Introduction to ADS-SFT Correspondence. Let's welcome him.
So thank you very much, and thanks for the invitation. And it's for me to be here. It's some special feeling since almost 24 years ago I was in ICTP in Swiss, Italy, but now we have a branch in Asia. And so here I would like to share some basic knowledge on ADS-SFT correspondence, and this has been given and lectured in several schools. But this time I prefer to use the PDF style here. And okay, and this is the non-story on ADS-SFT correspondence. I think the story started in 1970s. So we know I think most of you have known the black hole physics. So let me just give a very brief review. So this is the in 1970s, and Peking and Hawking they found that the black hole has entropy. So this is called the Peking-Hawking formula for Einstein gravity. So this entropy formula tells us actually the entropy of the black hole is proportional to the area of the horizon, not proportional to the volume. And so I put various constant in this formula. So you see here in the denominator we have h bar, and in the numerator we have this kd, this Boltzmann constant. And the presence of this h bar suggests that the entropy of the black hole is closely related to the quantum effect, not a classical notion. And this formula has a very important implication. It's the first, actually, it indicates that the quantum gravity somehow it has a fundamental principle in quantum gravity. So the degree of degree of freedom in quantum gravity, it has some holographic nature, and this has been proposed, formulated in 90s by Peul and Susskind, and the proposal is so-called the holographic principle. So this is its statement is that the quantum gravity is any volume. So you have a bulk and you have a volume, and it can be reformulated in terms of the degree of freedom as a boundary on some kind of the holographic screen, and so that means simply, as we know, this is holography, the movie, and we say that the bulk degree, or even the bulk dynamics, the physics in the bulk, can be reformulated by the degree of freedom on the holographic screen. So that's the holographic principle. So it's a principle, and it's a guiding principle. So it's not a precise statement, and to realize this holographic principle, it's not so easy. And in 1997, at the end of 1997, so this Juan Marcela found that he proposed this ADS-SFT correspondence. So this is loosely speaking, it means that the quantum gravity in a ADS bulk, in an ADS spacetime, is equivalent or is due to a conformal field theory at the ADS boundary. So this is a very loosely speaking. It's not a precise definition. The more precise definition will be given maybe tomorrow. And this is a very rough statement. And as we say, yeah, we have a bulk have a quantum gravity in ADS space-time, and we have a safety at ADS boundary. So it realized the holographic principle in the last slide. And what this correspondence has many implications. So these two are most important one. The first important implication is that this correspondence actually give a new definition of quantum gravity. So I will introduce a little bit of quantum gravity very soon. And so we have some traditional way to define quantum gravity. But this correspondence tells us we can't just define the quantum gravity by the conformal field theory at the ADS boundary. So that's a new kind of definition. And another important implication is that this duality actually is some kind of strong-weak duality. That means the safety side, if it's in strong coupling, then it's equivalent to gravity as a weak coupling. Vice versa, if we want to study some strong coupling problem in quantum gravity, you can apply the weakly coupling field theory. And using this strong weak duality, we can study various problems in quantum gravity, also in field theory. And this developed into a lot of branch, especially in applied ADS-FT correspondence, so-called the ADS-QCD, ADS condensed matter field theory, and etc. And so since its proposal in 1997, and its original paper has been cited more than 20,000 times. Yet now I think it's the most cited paper in physics. Yeah. Okay, and and as I mentioned, and the implication of ADS-FT not only in high energy physics, but it has extended to other branches in physics, like the ADS-QCD. This is the strong interaction and condensed matter, and sure, where some in quantum gravity, the black hole physics, and quite in the past decade, also it has close relation to the quantum information. And so we have using entanglement entropy to understand ADS-FT correspondence. Also, it has close relation to the fluid gravity correspondence. The people find that the usual equation of motion in fluid can be reformulated in the equation of motion in gravity. So that's a very interesting relation in this context. Okay, so you see that the ADS-FT has been applied to various branches in physics. So it's I think it will be still have very important implication in the future. Okay, and so that's a very okay. So if you have any question, please feel free to interrupt me. Okay. So any questions so far? Yeah. Okay. Let me go on. And so let's come back to ADS-FT. And from the point of view of a great physicist, Joe Pociński, he thought that this ADS-FT is the greatest equation ever we have. And so it takes this ADS-FT correspondence as an equation. On the left-hand side, we have the ADS quantum gravity. On the right-hand side, we have a conformal field theory. And so why this equation is so important? And so because that it contains all the central concepts in fundamental physics. So including, for example, for the safety side, if you take it as a super Yang-Mills, then that's Yang-Mills, it's a non-abelian extension of Maxwell equation. And also we have the on the field theory side, we have the fermion. We also have scalar. So we have Dirac equation and Klein-Gordon equation. And we have to take into account the quantum effect all of this field theory. So we have this quantum mechanics, quantum field theory, and gauge field theory. And on the left-hand side, we have the general relativity, and it's a quantum version. So it's a quantum gravity ADS. So and we have something more, and we have to apply some very attractive principle of nature. For example, the supersymmetry. Yeah, to define ADS-FT, we have to input supersymmetry from top-down approach, and the string theory. I think maybe Professor Lu has introduced string theory in the past 2 days, and extra dimension, and you will see that all these pinning principle of nature can be tied together in this framework. Even more, and this correspondence only it's as I mentioned, it's a concrete realization of holographic principle. The holographic principle could be, it could be more general. It can be applied to not only ADS spacetime. It can be applied to the flat spacetime, the theta spacetime. So this correspondence could be just a tip of a large iceberg, and so it can be deformed into a much larger set of the gauge gravity duality. So that's why Joe Pociński, he thought this equation or this correspondence is maybe the most important equation we have in fundamental physics. I will explain later in more detail. You will see that. Okay. Yeah. Okay. And so I think in the market we have various kinds of this duality, this gauge gravity duality. So how to establish this duality, this correspondence? So basically there are two approaches. One approach is we usually call the top-down approach. That means we start from a kind of quantum gravity theory, and from string theory, we're starting some brane system, and we take some decoupling limit, and then you will see we often get ADS spacetime, and then you get this ADS correspondence. So another approach is so-called the bottom-up approach. I will explain shortly. So in the top-down approach, we have to start from quantum gravity. So why we need to study quantum gravity? So this is, as we know, one of the most important questions in physics is to understand the quantum behavior of gravity. It's especially important in the early universe. So so we know we have a Big Bang singularity in classical general relativity. So you have this singularity theorem by Penrose and Hawking, and we know that we have a cosmological singularity at the beginning of our universe. And so around this singularity, the quantum effect could be extremely important. So, and we have to understand various quantum behavior of gravity near the cosmological singularity. And but if we try to study the quantum effect of gravity in the traditional way, I mean in the like in Euro gauge field or quantum field, you will get into trouble because that gravity is not normalizable if the space-time dimension is greater than 4, as the gravitational coupling constant is dimension 4. So this is so if you counting by some simple power counting, you will find that the gravity is not renormalizable in 4 dimensions and higher dimensions. And so this leads to a very important question. So what's the ultraviolet completion of gravity? So that means if you consider the gravity in very, very high energy level, then the Euro-Einstein gravity does not make sense. You have to take into account many corrections, infinite number of counter term in the very high level. So that means the gravity is not UV complete. So if you try to find a UV completion of gravity, then you have to find a theory of quantum gravity. So that what people has been working on since the 60s last century. So it has been a very long history, and moreover, if you believe Einstein's theorem, this grand unification in which all the interaction and the elementary particle can be unified in one framework, then you will say that the quantum gravity should realize the Einstein's theorem of grand unification. So we know that in particle physics, fundamental particle physics, we have this standard model. In cosmology, we also have a standard cosmological model. So, but gravity looks quite special. So, how to unify the gravity into that framework? So that is so-called the grand unification problem. And it believes that in a real quantum gravity theory, we will realize this grand unification. And so string theory or superstring theory. So it's a theory of quantum gravity. And I think Professor Lu should have introduced this to you. And there are five kinds of the well-defined productive superstring in 10 dimensions. This has been found in 1980s, and then the people realized that due to various kinds of the duality, these five kinds of the superstring theory are closely related to each other. It's only you can take it as a different color of a unified M theory in 11 dimensions. And then by studying the physics of this non-productive object, especially the deep branes or membranes in string theory or M theory, we can, from that approach, we can establish the ADS-FT correspondence. This is so-called the top-down approach. And so let me give you some example, a very simple example. So you will see that finally you will get this picture. And the superstring or M theory, we can simply call it the supergravity. In this spacetime, this ADS, in M+1 ADS spacetime cause p-dimensional compact manifold M, and here M plus p should be 9 or 10. If it's 9, it's superstring. If it's 10, it's M theory. And so this is supergravity in this spacetime is equivalent or due to a superconformal field theory in n dimension. So this is ADS boundary, n dimension. So that is, you see, it's a slightly more precise statement on ADS safety correspondence. And so in setup here, this compact manifold, you cannot choose arbitrarily. You will see that this compact manifold, the p-dimensional compact manifold, is closely related to the field content in the superconformal field theory. So it cannot be chosen freely, and you have to, you have to do it very carefully. And so let me give some example. And the most famous one, so this is the original discovered by Juan Madacena, is that the superstring, the type 2B superstring in this ADS5 cos S5. And now we take it, here it's M5, that is more general. And then it should be due to a 4-dimensional superconformal field theory. Usually it's a Yang-Mills theory and plus something else. And if this M5 is simply a five-dimensional sphere, then the superconformal field theory, it's an N=4 super-Yang-Mills theory. This super-Yang-Mills theory is conformal. So this is answer your question. And this is the most well-known and well-studied example in ADS-FT. And I will introduce this correspondence in more detail. And but if you take this M5, it's not a 5-dimensional sphere, but some other kind of Einstein manifold, 5-dimensional Einstein manifold like T11 or YPQ, and then you will get the superconformal field theory, the superconformal theory with net supersymmetry. So the supersymmetry is closely related to the this compact manifold. If it's a maximally symmetric space, then it's N=4. But if the compact manifold has less symmetries, then the supersymmetry will also reduce. And it's actually, I have to say, it's related to the isometry of this compact manifold. The isometry of this compact manifold related to the R symmetry of the supersymmetry. Okay. And so that's some technical stuff. Another important example is come from the D1, D5 system. And this also, this is quite important system, has played a very important role in studying the entropy of black hole in string theory. So from this system, one can precisely give a very macroscopic counting of the black hole entropy. So it's quite important. But if you also take some near horizon limit of D1, D5 system, you will find that it will lead you to a ADS3 cos S3 sector. And if you D1, D5 have something else, you have this 4-dimensional compact manifold. And so from this general statement, you will see that the dual CFT, it's a 2-dimension. It's in 2 dimensions. Also, it's a superconformal field theory. So it's some coset model. Okay. So this the first 2 examples is for string theory, but we can also think about M theory. So for M theory, then M plus P should be equal to 10. So you see that the total dimension to 11 dimensions. So from the study of M5 ring, you will get this ADS7 cos M4, and the M theory in this manifold could be due to a superconformal field theory in 6 dimensions. And but unfortunately, you see that one cannot write down the Lagrangian of this 6-dimensional superconformal field theory, since it has a tensor multiplet, and this tensor multiplet is self-filled, so it cannot be formulated into a Lagrangian. And in M theory, we also have another non-productive object. It's so-called M2 brane. So from this membrane, one can get this ADS4 cos M7. So M theory in ADS4 cos M7, and it's equivalent or it's due to a 3-dimensional superconformal field theory. So I think starting from the 2008, there are a lot of papers understanding this correspondence, especially when M7 is S7. Then we have this ABGM theory, another well-known and well-studied example in ADS-FT correspondence. Okay, and okay. So any question? Yeah. And let me give a few remarks. And I think here the example is not very precise. If you want to give a very precise statement, you will say that on the left-hand side, not only this space-time manifold, you have something more. Usually, there is usually a background field strength flux, and the presence of this flux backreact to your space-time and curve your space-time. So that's why you get this ADS spacetime and curved spacetime geometry. And also the presence of this background field string flux makes the study of the string theory and the M theory more difficult. So we have supersymmetry on both sides, as I emphasized before. And also I mentioned that the field content of superconformal field theory is closely related to the geometry of the compact manifold. So from different compact manifolds, the field strength, the field content in this superconformal field theory is different. So on the left-hand side, we have some kind of super quantum gravity, but usually we don't know how to study the quantum gravity in this ADS space-time. So the people often take the low energy limit to consider the low energy effective action of the superstring or M string or M theory. Then you will get a supergravity. That's the Einstein theory of a supergravity. That's the low energy effective action. And on the field theory side, usually originally it's a supersymmetry gauge theory. So then the people often call the ADS safety correspondence as the gauge gravity gauge correspondence. The gravity side is simply the Einstein gravity. On the safety side, we simply call the gauge theory, but this is not precise. So we will say in other examples, like in 2 dimensions. So there's no gauge theory; it's a coset model. So, but okay, but people often take the gravity gauge correspondence as another name for the ADS safety correspondence. Okay. And as you on the last slide, the top-down approach somehow is very restrictive. You have to start from some kind of the D brane system or M brane, and even though the gravity is UV complete, it's a well-defined quantum gravity. But if you take this top-down approach, you will see that you cannot, you only find a very restricted set of ADS correspondence, just listed in the last slide. And but on the other hand, we know the holographic principle is quite general. It should be applied not only to ADS spacetime, it should be also applied in flat spacetime, in the theta spacetime. And so that suggests that maybe we should take some other approach to understand the holography. Okay, so that's it. We call the bottom-up approach. So bottom-up approach, the most famous one is this ADS3 safety 2 correspondence, and this bottom-up approach, I think maybe I have to be careful. This is to study the asymptotic behavior of gravity. Is only maybe it's only one approach to get the ADS safety correspondence. And yeah, there's maybe some other approach like the tensor network and or like using the entanglement. Maybe there's some other way to understand to set up the ADS safety correspondence. And but here I introduce this the ADS3 safety 2. That its establishment is relies on the analysis of the asymptotic behavior of gravity. So here is the action of the ADS3 gravity. So this is the Einstein-Hilbert term plus cosmodal constant. And so we know that in 3 dimensions, the Einstein gravity, the pure Einstein gravity, has no dynamical degree of freedom. We have no gravitational wave in standard Einstein gravity in 3 dimensions. But nevertheless, we know that in 1986, Braun pointed out that even though we have no dynamical degree of freedom in 3 dimensions, but there could be some boundary degree of freedom, or sometimes it's called the global degree of freedom. And Actually, these two gentlemen found that under appropriate boundary conditions, the asymptotic symmetry group of ADS3 Einstein gravity is generated by two copies of Virasoro algebra with central charge, with this central charge. So it's proportional to the, this is the radius of the ADS and inversely proportional to the gravitational coupling constant. So what is the asymptotic symmetry group, this ASG? So it's okay. This relation is also simplified. It's some unknown symmetry modulo some trivial symmetry. So let me explain a little bit. So in this setup, you have to propose a set of boundary conditions as asymptotically radially asymptotical radial direction. But then you can try to find the diffeomorphism to preserve this asymptotic boundary condition. But some of these diffeomorphism could be trivial. So after you modulate these trivial symmetries, you will get the asymptotic symmetry group. But this treatment is quite subtle. You have to find appropriate boundary condition. So I have to emphasize appropriate boundary condition. Sometimes if your boundary condition is too loose, you can you find nothing interesting. But it's too restrictive. Also, this asymptotic symmetry group also is null. It have nothing interesting. So the asymptotic boundary condition is extremely important in this in this framework. Anyway, and Brown-Handel found a set of the appropriate boundary condition with non-trivial, non-trivial asymptotic symmetry group. It's generated by two copies of the Sorbonne algebra with this central charge, and for the relation between the central charge and the gravitational coupling constant, actually you will need something quite interesting. And in modern understanding, one can say that the quantum gravity in ADS3 is due to a two-dimensional holographic safety at ADS boundary. And more precisely, actually, I will comment very soon. More precisely, actually, this correspondence is only hold in the semi-classical limit. That means the semi-classical ADS3 gravity with Brown-Handel boundary condition is due to a two-dimensional holographic safety at large C. So semi-classical, that means this coupling constant, gravitational coupling constant is small. That means C should be large. So that is a holographic safety at large C only. Okay, and also I have some remarks. And the first most important one is that the pure ADS gravity itself is not a UV complete. So that means it itself cannot be a well-defined quantum gravity. This has been found pointed out by Maloney and Witten in 2007. Okay, I will not explain why it's not UV complete. It's also it's another long story. Moreover, the explicit construction of two-dimensional holographic safety is unknown. We don't know its explicit construction of two-dimensional safety. So it's different from ADS5 super Yang 4, we can write down the Lagrangian of four-dimensional n equal 4 super Yang. But for this holographic two-dimensional holographic safety, we don't know its explicit construction. And even though, nevertheless, we know that this holographic safety should satisfy some kind of property. For example, the Nazi holographic safety must have a sparse night spectrum. That means the night operator in CFT, its spectrum should be sparse. not very dense. So and that's what we know. Even though we don't know how to construct this two-dimensional holography explicitly, by using the so we know that a huge, there's a very large symmetry. It's a Virasoro symmetry. So in many cases in the study, due to the presence of this symmetry, we can still read out some universal property in this ADS3 safety2 correspondence. And another remarkable fact is that besides the Brown-Handel boundary condition, actually in three-dimensional gravity, there exists another set of the consistent asymptotic boundary conditions. This was found by Geoffrey Chompari, Wei Song, and Andy Strominger. So they called this the CSS boundary condition more than 10 years ago. And with this consistent asymptotic boundary condition, the ASG now is generated by Virasoro-Katsbudi algebra. It's not two copies of Virasoro algebra. It's a Virasoro algebra and a Katsbudi algebra. So Katsbudi algebra, it's a U1 current. So somehow for a Virasoro algebra, its global symmetry is SO2R. But for the Virasoro-Katsbudi algebra, its global symmetry is SO2R cos U1. So it's a less symmetric algebra. And this suggests that the semi-classical ADS gravity with this CSS boundary condition is due to a holographic warped safety. So with this kind of symmetry, the safety is not the Euro safety. So due to this U1 Katsbudi sector, so you will see that the safety is called so-called warped safety. There's some special property for this kind of safety. And so from this, then we say that the asymptotic boundary condition is extremely important. So with different asymptotic boundary condition, even though the action is the same, but in define a quantum gravity, the asymptotic boundary condition make a very important role. That's right. Yeah. Yeah, okay. So so that's the I think your question related to the first question. The pure ADS gravity is not UV complete, so you have to but semi-classically somehow semi-classically, that means you have somehow you can truncate your UV theory, truncate it to a semi-classical gravity, pure ADS pure gravity. And on the field theory side, you have this two-dimensional safety. Yeah. But that's not all. That's right. Yeah, that's right. So that's okay. So I have to show you the last statement. So this if you want to have a UV completion theory, then this correspondence should be embedded into the string theory. Yeah, this has been but you have something. You have this ADS3 cos S3 cos like S3 cos S1. Oh, that's another story. That's the central charge. It's I get your point. That's the world heat. What you mean is the world heat string theory. World string theory, but here it's so we have two safety. One is the world heat one, but here it's the holographic one. That's right. It's but you know. Right. So I mean here the if you okay, sorry. If you try to give UV completion with the three gravity, you have a kind of string theory. But this string theory you can define with a world heat conformal field theory, as you mentioned. It had a nice central charge. That's another string theory, the world heat safety. But the let me finish. The dual safety it's another. It's different from the world heat. It's another safety. Oh yeah, in 1+1 dimension, you have many conformal field theory. You have many conformal field theory. The central charge is due to the okay. Okay, we can discuss after a talk. Yeah, it's so okay. Yeah, and here I want to emphasize that the asymptotic boundary conditions are essential in defining a quantum gravity. This is a very important lesson from the setup of the ADS warp safety too. And so and there are some other examples where this bottom-up approach, and especially I think it's working out by the Andy Stormger's group, like in the context of the three-dimensional topological massive gravity, we have this warped ADS3 and warped conformal field theory, warped conformal safety 2 correspondence, and if we take some special limit, we'll get this flat holography. And in this case, we have still in active investigation in the past 10 years. And that are two proposals. One is the BMS, the colony safety. That's study the asymptotical symmetry group of the flat spacetime. You'll get this BMS group. So that people propose that the flat spacetime could be due to a BMS safety, the conformal field theory with a BMS group. And in higher dimension, you will see that this BMS group actually is also isomorphic to this Caronin group. So usually it's called the Caronin conformal field theory, due to a flat space time and quantum gravity. And there's another proposal is so-called synertial holography by studying the scattering amplitude in the flat space-time. And okay, that's also a long story. You can, if you are interested, you can find a lot of papers on this subject. And also by studying this asymptotic symmetry group stuff, the people establish Kerr safety correspondence, and that means the Kerr black hole in 4 dimensions, it could be described holographically by 2-dimensional conformal field theory. And also one can generalize this story to include not only pure gravity. You have to consider this high spin field included in the ADS gravity. In that case, the dual safety has more symmetry, not only the solar symmetry, it has this double symmetry. So this is also another interesting story. And along this line, the people realized that actually this ADS3 safety 2 correspondence could be embedded very nicely into the string theory. And also this is by Gabadieu, Matthias Gabadieu, and Rajesh Gopalkumar, they have been working on this for many years, and in the past few years, they have very nice proposal. on this ADS3 safety tool in string theory. Okay, so any other question? Yeah.
Can you explain more about the exercise? What the central charge? Can you explain more about it? What do you think you have the largest?
Central charge is okay. Here it's the central charge. Study the central symmetry group of this analyze. You say that the Virasoro algebra on the field theory side it should be related to the gravitational or inversely proportional to the gravitational coupling constant. And so semi-classically, this G is small and C should be large. So that's the large central charge. So it's not easy to construct a conformal field theory with a large central charge. But some people once proposed that this dual safety could be a Newell field theory. And Newell field theory could have a very large central charge. But Newell field theory is okay. It's quite complicated so that's why here I emphasize we don't know. There's no well accepted construction of this dual safety. Yeah, we only know it's some universal behavior that has a large central charge and a sparseness spectrum. That's all. Okay. So any other question? Okay. I'm a little bit slow. And okay, and in the remaining part of my talk, I will focus on the prototype of ADS safety correspondence. That's the original one. So this is the quantum gravity in ADS5 cross S5, equivalent to a super Yang-Mills in 4 dimensions. And this model has a very rich physics. So I just list quite a few. And the first one is a concrete realization of holographic principle. I have emphasized at the beginning of my talk. And also I will show you it evades the Weinberg-Witten no-go theorem and some other important idea in high-energy physics and also in string theory, like the this gauge group here is SUN, but you have to take larger limit. Oh, no, that's if n is small, then you will say that I will show you that it's the string coupling is related to 1 over n. So if n is small, that means the string coupling is very, very strong. So we don't know what it is. It's a special. So I'm sorry. It's even here. It's not a precise statement. I will give you a extremely precise statement. Yeah. Okay. And this you see, we have to take the. Yeah. Right. So you have. Yeah, that's I think in this top-down approach with supersymmetry, then you have some protection of the non-protective behavior. Yeah. Without supersymmetry, you will get somehow get lost. Not lose control of many things. Yeah. Okay. I have no idea. Yeah, of your question. I don't know the answer. If you can twist it into a topological string and something else. Okay, one thing I can say is for the scaling amplitude stuff. Yeah, the people can do some twist and like the twister string and related to the scaling amplitude, but it's different context. Okay. Okay. I have 1 minute. Okay, I'm sorry. Maybe I explain this two points. Yeah. Okay. And so what's the Weinberg-Witten logo theorem? This is also it's a very strong logo theorem. So the question that in the 1970s, the people try to think this question: if the spin-2 graviton is a bound state of 2 spin-1 gauge boson, okay, the answer is no. If we have local Lorentz symmetry and conserved energy momentum tensor, this is impossible. That means this graviton cannot be the bound state of 2 spin-1 gauge boson. So this is the Weinberg-Witten theorem, logo theorem proposed in 1980. But we know the more powerful a logo theorem, the deeper its counterexample. So for supersymmetry, it gave a very concrete realization of this statement. So we know that in supersymmetry case, we have this Korman-Manduna theorem. But if we know the graded algebra, then we can extend the symmetry of the S matrix into supersymmetry. So that means the Korman-Manduna theorem should be generalized if we have the graded algebra. So then how to evade this Weinberg-Witten logo theory? And there's some underlying assumption. The underlying assumption of this logo theorem is that the graviton bound state moves in the same space-time as gauge boson constitute. So that means if we consider the 4-dimensional gauge field theory, this theorem actually forbids the graviton bound state in 4 dimensions. But now the ADS-FT correspondence bypass this logo theorem in a very clever way. Yeah. Now the graviton is not in 4 dimensions. It's in some extra dimension. So the graviton should move in 1 additional dimension. So so this is a very clever way to bypass this logo theory. Okay. So let me explain a little bit of this larger limit of the Hooft's very that's in string theory. So here it's I mean it's in the assumption that the graviton bound state and its gauge boson constitute in field theory. So in field theory, you have this symmetry, Lorentz symmetry, and the conserved energy momentum tensor. Okay, then it's impossible. Okay, in string theory, it's another story. Yeah. Okay, the larger limit of Yang-Mills, it's in 1970s. The Hooft noticed that, and this larger limit of Yang-Mills could be a string theory. So this using some very clever way to study the Feynman diagram. Now it's called the double line trick. So I have to say, we consider the pure Yang-Mills, and the gauge field is in the adjoint representation. Then the adjoint representation can be realized by the double line. So we say that you have these two Aij, so, and more precisely, you have to say A mu Pij. Okay, A mu. You have this Pij star, right? And A mu and A and PAIJ star. And so it's called A mu Ij. And then the propagator you can say one is I, another is J. So this is so-called double line representation. A double line representation. And using this double line trick, each diagram can be reorganized into this kind of form. So this is a propagator. You have this T square. The number of propagator you have this. Each propagator has T square. So if in a Feynman diagram you have the number of a bunch of propagator, you have this T square number of propagator. And you have a vertex. This is the coupling, the 3 vertices or 4 vertices. And you have the G1 over T square. So you have this -1. And you have, if you have a loop, you have to take trace. So if you take trace, you have a factor n. So you have this number of loops. You have n power of a number of loops. And then you can reorganize the first line and take this n and put the other factor of n into G square n. So then you say this number of loops, you can take it as a number of phase. And for the number of propagator, you have the number of edge. So this is minus, you have n here, you have another n here. And for the vertices, still vertices, now it's plus. And so so you say that in the bracket, somehow you have a topological number. This is called Euler number of the Riemann surface, of a 2-dimensional surface. So it's a no supersymmetry. It's a pure Yang-Mills. It's pure Yang-Mills. And you see that this is for the nth power is 2 minus 2h. 2 plus 2h is a topological number. And h is the genus of a Riemann surface. So this is the Euler number. So I think you should know in the high school. And then in general, the partition function could be using this organization. Then you say that the partition function could be written this way, and you have this factor nth power 2 minus 2h, and some other function of this G square n. And to Hooft proposed that we can take this large n limit, then n tends to infinity, but keep this factor G square n as a 't Hooft coupling being fixed. Okay, this is so-called the 't Hooft limit. Under this 't Hooft limit, then this partition function looks like the string theory, the partition function of the string theory. And so in this large n limit, you see that you can focus on the first term when h equal to 0, that is dominant. So h0 means that the planar diagram dominates in the 't Hooft limit. Okay, okay, and also we say that if you compare with the Riemann surface, the genus of a general Riemann surface, and also compare with the string interaction, you will say that the genus and this factor, the genus, the number of genus is related to the string interaction and vertex. So that suggests that inspired 't Hooft to propose that the large n limit of Yang-Mills is a string theory, and also the string coupling and the GS is related to 1 over n. So so if you want to define a string theory, and in general, if n is too small, then that means you have a very, very strong string interaction. So we don't know. Yeah. Okay. But we know the 4-dimensional Yang-Mills. If you ask this question, is 4-dimensional Yang-Mills is a string theory? But we know it's in 4 dimensions. But the string theory, as emphasized by Professor Lu, it should be in 10 dimensions if we have supersymmetry. And so that means this cannot be so simple. And it cannot be a string theory in 4 dimensions. And Polyakov and 8 dimensions. Okay, so pardon?
Octonian.
Octonian. Okay, so this is actually, Polyakov, even before the ADS-safety correspondence, and Polyakov and his collaborators, try to realize the 't Hooft idea, and they showed that there must be at least one more dimension. At that time, they proposed that the extra dimension should be a neural direction, a kind of neural field theory. But that kind of string theory is very, complicated, and still some people still working on that stuff. Anyway, the important point is that four-dimensional super-Yang cannot be simply a string theory in 4 dimensions. If you have some other extra dimension, there should be something more. Okay, this is a very important point. And the above discussing a matrix model on Yang-Mills actually can be applied to other matrix valued field theory. Actually, we see that it's depending on the field theory in the adjoint representation. So if you consider any kind of the matrix, so it's a matrix value. So for the matrix valued field theory, this larger limit could work, right? And actually, this has been discussed in 1990s. For example, if we consider a pure matrix model, it could be due to a minimal string theory. That means minimal model plus some neural theory. And if you consider a time direction, that means we study the matrix quantum mechanics, and it could be due to a 1+1 dimensional non-critical string. And this has been studied in 1990s before ADS safety correspondence. Also, if this gauge group could be not SUN, it's SON or USP2N, then the same study will lead you to the non-orientable string. And also in string theory, you will see that it's true. If you study the non-orientable string, the gauge group SON and USP2N will appear. Okay. Okay. Maybe I can stop here and we can continue tomorrow. Okay.
So let's thank Professor Chen. Thanks for questions. Quick questions.
Yeah.
Because we have enough questions. Very short questions.
May I ask, can we embed some lower dimensional ADS safety into some higher dimension one? For example, for ADS to safety 1 into ADS for safety 3?
Oh, yeah, I don't think so. The people try to study to embed the ADS2 like the SYK and into some more stuff, but still ADS2 factor still there, but some other factor like ADS2 cos S2 or cos S3, yeah, but not ADS4. Yeah, so I mean the topology is quite different. Yeah.
Okay, thank you.
So I forgot to mention in the beginning, Professor Chen, he was a postdoc fellow at ICTP.
ICTP, yeah, more than
many years
20
ago.
years ago.
Yeah. So he has very close relation with ICTP.
That's
Let's
right.
thank Professor Chen again.
Okay, thank you.
Okay, let's take a few minute break. Now we're going to prepare for the next lecture.
多谢陈老师。
没有，不客气。用英语讲还是不行。
没关系，
没问题。行，那明天还是时间。
好的。 还是不给我？
哦，
我插上你这个不就行了？
对，它好像没有这个头，我把这个
不，我有这个头，我赶紧拿下。
哎，有，这有个 USB， 是吴老师用 USB 吗？
不是，它是这个 Type C 的口。
Type C 这有一个口
啊，有一个口啊。
，Type C 也有。
是这个。
我不知道啊。
我忘了。
你这个不是我的，
不是。
不是吗？
你看这个还没上去啊？可能你没连上去。
对，这地盘。
地盘。
可电脑，然后看看。
地盘。
在这个，哎，不对呀，没有啊。
地盘有地盘。
地盘是我们的，是我们自己的。
这没有反应。
有吗？这个小键谱这里没有。看有没有额外的，对。没有，不识别。我直接先把这个。
对，先考上。直接
插上去吗？
不会，因为这个没。
哎，有了。
那为什么这个不插？
这个不知道，这个我不知道是语言什么的，这个有没有？
那吴老师，您能先考到电脑吗？
先考到这个。
你这个盘在哪里？啊，在这个。
然后
这个
是右键，这是左键。
就已经是这个您的文件夹。
OK， 对，那你就是这个。
就这两个。
对呀。
直接Ctrl+C Ctrl+V 就行。
对，你这个多了。你是苹果的吗？
不是，Ctrl+C 就行。
它是这个
PPT。
其实话筒，你看别在哪？
你这是网上的？
对，我们在网上直播，然后就是
网上直播它，
激光笔。
所以你现在有外宾吗？你用中文的，好吧？好吧。
有几个外宾？
好吧。
您说中文没问题。
不，我今天我这英文好了，也许但有的播的时候讲中文。
好。Okay, let's continue. So for the second lecture of this morning session, we're delighted to have Professor Yueliang Wu. He's director of our institute ICTP-AP, and Professor Yueliang Wu is also the academician of the Chinese Academy of Sciences. He's a great expert in quantum field theory and particle physics. And also recently, he's working on the hyperunified theory. So let's welcome him.
Okay, good morning. So let's together the first lectures about unification with gravitational quantum field theory. So the contents including 3 parts. The one, I will briefly introduce the current challenge in the general relativity and quantum field theory. And then I will talk about the gravitational quantum field theory, how to merging general relativity and quantum field theory. And then we see within this framework of gravitational quantum theory, how to build the hyperunified field theory to unify all the fundamental interactions. So our current understanding on elemental particle physics, okay, we know the discovery of Higgs boson in 2012, so which means the last predicted particles in standard model. Okay. The total in the standard model, there's 61 particles. So here is about the fundamental particles for the leptons and quarks, which constitute our universe. And then there's some interacting particles like the photon, electron weak boson, and gluon, and also the Higgs boson. So the only undiscovered elemental particles is graviton, which is predicted in the quantum gravitational series. Okay, then what is our current understanding on universe? So a basic picture about the universe. So from the astronomical observation, the early universe past inflation, and then the basic constant of universe include the dark energy, dark matter, and also atomic matter, quark matter. So we know you may already hear that the dark energy is about 70% of energy of the universe, and also the matter about 30%. Among them, more than 85% is dark matter, and the quark matter or atomic matter is about 15%. The total, we know the dark matter is about 25%. Okay, the atomic matter is less than 5%. So that means our understanding on the nature of the universe is very limited. So more than 95% is still unknown, although the astronomical they observed the effect, but their nature we still unknown. Okay. Well, as I mentioned, the only unknown particle and an observed particle is graviton, where the 2016 LIGO announced the direct observation of gravitational wave. So we believe the gravitational wave composed of the graviton. So the discovery of gravitational waves so provide a more fundamental test to the general relativity, and so also bring us to study more deeply the nature of space-time and gravity. But we know the early universe
is actually our universe in the very high temperature and energies. So it should be the state of elemental particles. So in that time, the quantum gravity should be applied the more important rules. Okay. So the most challenging problems in this century is to understand the nature of gravity, and also our so that we can understand the origin of the universe. And then we want to expand the puzzles of dark energy and dark matter, and that needs us to establish the unified theory for all basic forces, so that we can explore the laws relating very small elemental particles and also the extremely large universe. So what is the fundamental challenge? So the question for the successful combination of general relativity and also the quantum field theory, so that how to unify all the basic forces. So actually this is the most challenging things. But we know the three basic forces of electroweak and strong interaction in the standard model. It is well described by quantum field theory with the symmetries. We call the 1, 2, 3 symmetries, which govern the electromagnetic interaction, weak interaction, and the strong interaction. They all can be described by the quantum field theory. So that's what is quantum field theory? So we just combine the spatial relativity and the quantum mechanics. Okay. Then plus symmetry, as mentioned, is the 1, 2 symmetry. And then our observed universe, so it's the rich universe actually is after the symmetry broken, and all particles receive masses. So then we will ask what is basic symmetry for gravity, for example. Yeah. And the general relativity of gravity, be it based on geometry, is also very successful. So actually up to now, all observable effects can be described by general relativity in the universe. And the general relativity based on the foundation is about the general covariance. That means the physical laws of nature are to be expressed by the equation, which mainly dominated by the dynamics of the space-time or coordinates, and then by this so-called curvature tensor. So we now, so in that sense, the Einstein's general relativity, general theory of relativity, revolutionized our understanding of space-time, and which actually replaced the classical Newton's idea about absolute space and time, and also introduced the concept of space-time as a dynamic one, and use the curved space-time to describe the gravity. Okay, so although the general relativity alter our understanding of basic interactions between all the massive objects, okay, but replaced Newton's the concept of instantaneous action at a distance. Yeah. Where Einstein's general relativity didn't challenge the Newton's hypothesis that all the massive objects are assumed to be indivisible and point-like particles, like a mathematical point. So there's no energy structure. We only need to know the energy momentum, and so on. So that means in general relativity, it doesn't care about the intrinsic structure of matter. Okay, so this is still the same as the Newton theory. Okay, its basic assumption in Newton theory is postulate all the massive objects to be a point, mathematical point. Then you can use the Newton law to describe all the motion of matter interactions. And then what is the limitation of the general relativity? So actually, so this anti-equations. The left-hand side is geometry, right-hand side is energy momentum. So the energy momentum, maybe I think it's like a mass, the momentum or distribution of matter, but it does not matter about the intrinsic structure. Okay, but it's revolutionary because in that time, that means in 1915, so we only know special relativity, Newton's law, and maybe we already have some atomic models from Niels Bohr, and the idea of quantization. But we don't know how the electron or how even we don't know electron, so we don't know the quantum mechanics. So we don't know the elemental particles. So in that time, generalize special relativity to general relativity to describe the gravity is revolutionary. And then when I was 100 years ago, so when Max Born suggests the quantum mechanics, and then Heisenberg and Schrödinger and established matrix theory or the wave functions and so on. So we know how to describe the fundamental particles like electron. Okay, so they use the wave functions in no relative quantum mechanics. And then 1 year after or 2 years after, so Dirac combined special relativity with quantum mechanics and to see how to describe an electron. So we know there's the Dirac equations. Okay, so that's is called the relativity quantum mechanics. Okay, and then you will find that the single wave function in Schrödinger equation must be replaced by the 4 complex component electron wave functions. Then we will ask why the 4 complex component. That means there's 8 independent degrees of freedom instead of 1 complex wave function. Why is 4? So the 4 is actually when you combine the special relativity and the quantum mechanics, we require the Lorentz symmetry. So Lorentz symmetry is for a 4 space-time dimension. Okay, so then you want to have the Lorentz symmetry for both coordinates and wave function together. You get the Lorentz symmetry. So this is why we need the 4 component of this wave function instead of 1 single complex one in Schrödinger equation. So that's very important observation or important for the Dirac equation. I think in the sense, the dimension of space-time determine the component of the electron wave function or determine the independent degrees of freedom of the electron. That means the space-time dimension related to the matter, the intrinsic structure. I think this equation, Dirac equation, and also you see the Einstein equation, both are very important. They relate to the geometry, energy momentum, and here is the dimension of space-time and the intrinsic structure of the matter. So both are very important. And based on this relativity quantum mechanics to develop the quantum field theories and establish standard model to describe electroweak interaction and strong interactions. So now both theories for general relativity to describe a micro world, and for the quantum mechanics to describe the macro world. Yeah, both for very small elemental particles and extremely large universe with these 2 equations. So the question how to combine these 2. So that is the question actually. So for quantum mechanics, we now, yeah, so 100 years ago, next year we will celebrate the International Year of Quantum Science and Technology. So from Heisenberg, the Max Born, Jordan, and the Schrödinger and the Dirac, I say. So this for the quantum mechanics. And then to the quantum electrodynamics and quantum field theories, the QED, for example, from this with Tomonaga, String, and Feynman, and the contribution from Dyson, and so on. So actually, this quantum field theory started from the quantum electrodynamics. And then we have the Yang-Mills gauge theory and the polarity no conservation, which gave the basic framework to establish the electron-weak interactions. Okay, it's like the Grash, Weinberg, the Salamos, the Yang-Mills, and the TGV and Stern Yang and the CS Wu experiment, and then to the quantum chromodynamics for strong interactions. Okay, and for the asymptotic freedom and also three colors. So the contributions from the Damgaard, Rechek, Polita, and like Fritzsche Gamma and Laurent and so on. So that's a lot of. And then next they come to the ground unified series to unify the three basic forces, electron weak and strong interactions, like George Glashow and Friedrich Minkowski and so on. The SU5, SU10, yeah, for now, the minimum unification. And then from universe, we have the influence of universe, like Star Robinsky, Gould, and Linda for inflationary theory. And then we also now understand that what is the basic constant of matter, the quark model. 60 years ago, 1964, by Gamma, they introduced quark models. And then we are also the dark energy, which has more than 95%. Okay, and now. And then for gravity, so although the gravity is the first, I think the force we recognize the mechanism, but we don't understand it well. So the gravity described by the geometry, Riemannian geometry, in the cavity space-time. But then people after the Yang-Mills theory, many people to think about maybe gravity is a gauge theory. Yeah. So this is early years from Uchiyama, yeah, so 1956. So there's a lot of studies about the gauge theory of gravity. But most of these discussions is still based on the curved space-time. Just for the formulations are very similar to the gauge theories, and because the general linear group is a group, so there's some fine connection and so on to relate to the gauge theories. So most of them still based on the space-time, the coordinate space-times. Okay, it's not started from matter, the intrinsic nature of matter. Okay. So then there's some open questions with what is the definition of space-time and the basic structure of Lagrange or dynamic properties of the gravity gauge, actually, in these discussions. Okay, so actually the quantum mechanics and the quantum field theories, I said the Einstein theory is we know is already abounding the Newton's idea, but that's the most important the Newton's concept of point particles. So there's no in the general relativities is still problems. Of course, there's one extension we know, as also our previous speakers, the string theory. So extend the point particles, one-dimensional string. So this is one step to extend the Newton's idea, the Newton's concept of point particle. But actually, quantum mechanics and also quantum field theory is already extend Newton's idea from another side. They extend the point particle to field, a quantum field. Okay, so this is another extension. But from string theory, you further extend the point particle to one-dimensional object, and then to develop the string field theory. Yeah, and that's based on the string, not not based on the coordinate distribution, based on strings distribution. But both actually is already extended the concept of point particle. The question is whether we need, we directly extend the point particle to the field, the quantum field, or we need to extend the point particle to one-dimensional string, and then to further extend the string to string field theory. Okay. So that's I think we need to discuss. But it's actually string theory is very beautiful, yeah, mathematically. Then of question, we will say why we extend the point particle to one-dimensional string, why not to two-dimensional, three-dimensional objects, then to field theory. On the other hand, if you extend the point particle to the one-dimensional or either two-dimensional, three-dimensional objects, then further extend to the field theory. So you have two steps. That's why make I mean very complicated mathematics. Okay, also complicated some technique to do. But anyway, we know the string theory not only for string theory for unification, but also have a lot of applications from string theory. Our previous speaks already discussed a lot, especially like string QCD, so IDS QCD and so on. Of course, string theory originally also motivated from QCD string, you see. So once for string interactions, very strong interactions, and the grounds, the exchange ground for the strong interactions, if in low energy, there's no perturbative interaction, very strong, this grounds like string. Okay, so this is why we first have QCD string and then extend to the fundamental string. Okay, this some history maybe Professor Roux or Chen, they are all expert to discuss that one. Here we just discuss the quantum field theory to extend the Newton's concept of point particle, just direct from point particle to the field, to the quantum field. Okay, so the standard model of quantum field theory is based on this framework. So there's leptons and quarks as a quantum field in the standard model. Then they have some intrinsic structures which characterize the symmetries, or that means their independent degree of freedom or the quantum numbers determine the symmetry. Okay, and then when you gauge these symmetries, you introduce gauge field. So this gauge field as the messengers to to propagate and to understand the interactions. Okay, so this quantum numbers actually include like Helix spin, the Bohr spin, or chirality spin, charge spin, iso spin, color spin. Yeah, as for the charge spin for the electromagnetic interaction, iso spin for weak interaction, the color spin for the strong interactions. But we still have some chirality spin, Helix spin, Bohr spin. They are still global. So this in the quantum theory, this global symmetry and associated with the coordinate symmetry as a Laurent symmetry. So that is the framework of quantum field theory based on special relativity and quantum mechanics. Okay. Okay, so this we see the symmetry is very important. Why symmetry is very important? So they cover all the interactions. But how we don't know how this symmetry comes from? Is it from quantum number or from the intrinsic structure of quantum field? Okay. So then we will ask the basic issue is what is the symmetry indicated from quantum number of leptons and quarks for gravitational interaction? Okay. So we know all the matter have gravitational interaction, and how we know the fundamental constituent of matter is leptons and quarks. Then we will ask how leptons and quarks have a gravitational interaction. So how introduce gravitational interaction for leptons and quarks? That means we start from leptons and quarks, the basic constant of matter. We do not start from coordinate, from geometry. So that is general relativity of Einstein in his time. 因为 because that time we only know general relativity, special relativity, then extended special relativity, the symmetries or coordinates. But now we now have leptons and quarks. We know their symmetries, their quantum numbers. So we should start from the leptons and quarks. So this is the actual basic idea for gravitational quantum field theories, and also this paper I'm going to discuss actually. So for gravitational quantum theory, we will see how the presence of intrinsic structure and the relevant symmetries in quantum field theory, quantum field of leptons and quarks. Okay, and then we shall challenge Einstein's equivalence principle in general relativity. That's just from the geometry, coordinate, and from mass. I mean, from this point particles, the mass and energy only, not the intrinsic structure. So this our basic consideration start from leptons quarks in standard model. So we say, okay, the gauge theory of free gravity is constructed within the framework of quantum field theory based on the globally flat Minkowski spacetime. We do not start from the cavity spacetime at the beginning. Okay, then we treat the gravitational force on the same footing as the other three basic forces, electron, weak, and strong induction in standard model, and based on quantum field theory in flat Minkowski spacetime. So we start from flat Minkowski spacetime. So very important for that one is we have to distinguish group symmetries in the Hilbert space of quantum field. That means for leptons quarks, and the group symmetries in this globally flat Minkowski spacetime of coordinates. We have to distinguish these two symmetries. But in special relativity, in the quantum mechanics or in the quantum field theories, we do not distinguish the symmetries of the leptons quarks in the Hilbert space and the symmetries in the flat Minkowski space. They have to be associated. Okay, so this is why these symmetries are associated with the same symmetries. Okay, so our basic assumption is that we suppose the basic constant of matter is the quantum field of the Dirac type spinor or Weyl type spinors. But actually, in the standard model, all the fermions are Weyl fermion. Weyl type fermion is not Dirac type fermions. But when Dirac discussed the quantum mechanics or for the quantum electron dynamics, all the electrons they behave like Dirac fermions because they have no weak induction. Because in the weak inductions, all the fermions is Weyl fermions, distinguish left-handed and right-handed. Okay, so when we consider both electron weak interactions, so all the fermions must be Weyl type fermions, the carrier fermions. And then we say the kinematics of all quantum field should obey the principles of special relativity and quantum mechanics. And the dynamics of all quantum field is characterized. So when we consider both electron weak interactions, so all the fermions must be the carrier fermions. And then we say the kinematics of all quantum field should obey the principles of special relativity and quantum mechanics. And the dynamics of all quantum field is characterized by the basic interactions governed by the gauge symmetry. So this is the basic assumption in the quantum field theory. Okay. Then when you do the spin symmetry in the Hilbert space of spinor field and the Laurent symmetry in the Minkowski spacetimes. So we take this spin symmetry as gauge symmetry. Then we have to introduce the idea is called the biafram spacetime. Okay. That means The coordinate space-time is the base space-time, and in spin, there's also factors in the in spin-related space-time. We call the spin-related space-time is a kind of intrinsic space-time, and in this space-time is local flat, okay, and this is global flat, and then we have to use this biframe space-time concept for the gravitational quantum field theory. As the one frame is still flat Minkowski space-time of coordinate, which act as an initial reference frame for describing the motion of the basic field. So this actually is a base space-time. And another one is spin-related that we will introduce later on. We call the gravity gauge space-time, so which functions as an intrinsic interacting frame for describing dynamics of basic field. Okay, so this locally flat, no coordinate space-time as spin-related, we will see it is no commutative geometry. So that's no commutative property describe the gravitational effect. Okay, so in this space-time, we have to introduce bicovariant factor field. In the coordinate space-time is a factor by this index mu, and this A is in the spin-related space-time, gravity gauge space-time. So they're all from 0, 1, 2, 3, and the time plus source for space-time. Rather than for the metric in the coordinate space-time, so describe the gravity, so in the general relativity by this tensor, okay? So this I call the bicovariant factor field in both in the base space-time. So this is the tensor factor in the coordinate space-time, in the curved space-time, okay? So that's the difference, okay? Okay, so how this spin-related gravity gauge space-time relate to the coordinate space-time? Then we have to introduce a field, okay? So this coordinate space-time displacement, this we call the displacement in the spin-related intrinsic gravity gauge space-time. So they related by this field. So then coordinate, you still have some Lorentz symmetry, global Lorentz symmetry. But this one allows to have a local spin gauge symmetry, okay? So both are factor. So this is coordinate factor. This is spin-related factor. Okay, so this I call this for the operator, for the derivatives. This is dual to this one, this function. So they are not independent. The dual means they satisfy the dual conditions for the orthogonal one. Okay, you see. Okay, then we can define the composite graphmetric field. The Einstein in Einstein theory, this is tensor in coordinate space-time. It's actually like metric. So this combined by this gravity gauge field, bicovariant factors, when you contract this index of spin. So in this one, you see there's no intrinsic structure indicated in this metric field. But here, if we want to consider as the composite field, so actually spin, I mean the intrinsic structure is become hidden, okay? So now we can see when you have these definitions, you do these commutation relations, we found there's not commute. But the coordinates, the partial mu, and equal to 0, they commute. But for this one, it's not commute. So you introduce a group structure factor. If we regard this as like an algebra of group, okay? So this is like a group structure factor. So this group structure factor is given by this field. So this maybe you're familiar if you study electrodynamics, okay, quantum electrodynamics. This is like a field strength. This is like gauge field, okay, but it has 4 gauge field in the spin-related space-time instead of 1 in the Maxwell equation. So you have 4, okay, this is like field strength, okay. So then you project it to the spin-related space is given by this relation. So now the details to describe the graphic dynamics and spinor dynamics and the electrodynamics in this gravitational quantum field theory, so as examples. And you will find now we have symmetries. So this symmetry is translational one, is this Laurent symmetry. Rotational one is called Damgaard symmetry. And in the spin related space-time, you have a rotational spin symmetry, and also the translation like I call the internal translation like symmetry. Okay. Okay, so this we call that I call this actually is chirality both spin symmetry. The translation like one is rotational spin symmetry. So then we separate these two symmetries. We have to introduce this field. So this for the coordinate space, the Laurent Damgaard symmetries. So in this spin-related space-time, we have this inhomogeneous spin symmetries. Okay. Then we can construct the action Lagrange. When we have Lagrange, you know how to do all things. Yeah. So in the spin-related space-time, we can directly construct the action, for example, for this chiral representation electrons. Okay, so then you see, so this, for example, like electron magnetic interactions. So this is spin interactions. So this term is gave the mass of the spin gauge bosons. This term gave actually eventually gave the gravitational interaction. But I all represented them in the spin-related spacetime. Is not in the coordinate spacetime. So in general, it's coordinate independent. But you can project it to the coordinate spacetime by use this graphic gauge field I mentioned, this one. So this actually like a ghost boson, Ghoson type boson. You can project it to the coordinate spacetime. You can also project it to the spin-related spacetime. So as this is ghost boson, okay, so it's always massless. So this is why the graviton, when you use this one, is always massless graviton. Okay. Okay, then you project the space-time. Okay, you find the electromagnetic interaction and the spin gauge interaction, and this gives to the mass time of spin actually. So this gravitational induction. How we know this goes to gravitational induction. Okay. So this is called the biform space-time, the spin-related space-time, and you can project to coordinate space-time, and so on. And as because this is coordinate independent, eventually we prove that. So when you project to the coordinate space-time, I start from flat Minkowski space-time, but actually we found there's a hidden symmetry as it is independent of coordinate, so you can have any symmetry. But then eventually you find there's a hidden general linear group symmetry. So that is the foundation of Einstein general relativity. So then you will ask if we use the graphic gauge field as the basic gravitational field, how could we derive the Einstein equation? But we know the Einstein equation, general relativity, is well established and tested by experiment. So we have to derive it that one. Okay. So that means in general, this Lagrange has the hidden symmetry. This actually is general linear group symmetry of coordinates. But that means, on the other hand, it's different from general relativity. So I start from flat Minkowski spacetime, and then we can find there's general linear group symmetry as the foundation of general relativity. That means in this theory, we can always choose flat Minkowski spacetime. But if in the general relativity, you can only locally choose a flat spacetime. But here, in the gravitational quantum theory, you can choose globally flat Minkowski spacetime as a base spacetime. Okay, it's not a local one. So that is actually different from the. And you will see this term as actually beyond the general relativity. There's some new effects. This term. Okay, then from this background, you can use the least action principle to derive the Dirac equations and then the Dirac equation in flat spacetime. So when you have gravitational interaction, it extends to this one. Okay, with this covariant derivative include the spin gauge symmetry, and you have this graph gauge field. Okay, and then you will use this graph gauge field, derive the gauge type of gravitational interaction, gravitational equations with conserved current. Okay, this is the gauge theory. It's real gauge theory, gravitational, the gauge interaction, the gauge theories. You can where to find this one. Okay, and you will ask how these equations from this equation to derive the Einstein equation, because the general relativity is well established and tested by experiment. Okay, we just start from these equations, then to project this spin-related space-time to the coordinate space-time by using this graph gauge field. And then you will get two equations. Because this equation is because this is 4 times 4, 16 equation of equations. 4 times 4 is 16, okay? But the Einstein equation is only 10, you know? So then the 16th, you have 10 symmetric one, and the 6 anti-symmetric one. So 10 symmetric one is generalized Einstein equation. So because I have this term, this tilt, so this time because I included the spin gauge, and also include I didn't write down this. I didn't write down this this current, because you see, I can prove this one. This can be proved exactly as Einstein-Hilbert action plus the total derivative. So this is equivalent to the Einstein-Hilbert equation. But these two terms, the spin gauge field and this relate to the mass of spin gauge field, but it's spin gauge invariant. One including the gravitational interaction, you can construct a spin gauge invariant terms. So this additional terms to generalize the Einstein's equation. This I call the T-tiered actually. So you have this one, the T-tiered term. So this is normal, is the energy momentum tensor of the like electron magnetic term and the electron term, yeah. And then there's an anti-symmetric part that is beyond the Einstein equation. So then we have this one for anti-symmetric one, for 6 anti-symmetric one. So then if suppose the spin gauge should be heavy, otherwise we should observe it by our collider experiment. So the spin gauge field should be heavy. And if spin gauge field is decoupled, then we have only electromagnetic, and then there is additional term. That is actually from this, I mean, the spin gauge mass terms. Okay, these terms actually is different. Even you have only electromagnetic, and then have graph gauge field, then you will find that's additional term. That term is related to the spin gauge. Okay. Even when spin gauge decoupled, the still term is given by the graph gauge field. So this term, when you linearize the Einstein equation, the generalized Einstein equation, so these are 2.2 is Ouevedo is gravitational like the, so that like a field strands. And if I gave by this fact. Because I finalize these are the job gravitational field what yeah, and the B had an electron. This guy, you know, this one. Max equation polarized speed. It's different from this normally in our Max equation. E hat E only depends on E polarized depends on E, and the B is polarized with this B. Okay, I know that you can also write the different ways for Max equation. I have no time to discuss here. So maybe how long times? 5 minutes. Okay, but anyway, I have another another lecture. Okay, so the conclusion for this gravitational quantum theory. I don't know if because I know I have 2 lectures, so I just speak slowly to clarify this quantum field theory and gravitational quantum field theory. Okay, here I say it's essential to distinguish the inhomogeneous spin symmetry in the Hilbert space of matter field, like Dapton Park, with the inhomogeneous Lorentz or Poincare symmetry in coordinate spacetime. And then the laws of nature always gauge invariant principle. And then we have this automatically have this hidden group symmetry. So in the biframe spacetime, and then we say the gravitational quantum field theory provide a new approach for consistently combine the general relativity and quantum field theory. So this can provide us a unified theoretical framework to describe the 4 basic forces. And then we see how to unify the 4 basic forces. So here's provided the framework of gravitational quantum field. So this may be, if I have no time, so maybe I go to, or I just give some ideas and leave to the next lectures. So idea now is very simple. So with this gravitational quantum field theory, this framework. So as I'm already emphasized before, so from Dirac equation, what gave us some intuitive, ideas. So this Dirac equation, how actually provide some correlation between quantum number and the geometry or dimension of spacetime. Okay, and the 4-dimensional spacetime of coordinates determine the 4-component entity of Dirac spinors. Okay, so now to unify, okay, all the interactions is very simple. We just go another way side, yeah, another way. So that means now in the quantum field theory, so we know electrons. And then from then we want to describe the electron by the relative quantum mechanics. And then we found the 4-dimensional space-time determine the 4 components. So now we already know the electron, neutrino, and the quark, and they also have the solid formulas, okay? And all these elemental, we know 48 elementals in the standard model. And we have to count the independent degree of freedom. How many independent degree of freedom? How many quantum numbers? So we now have charge spin number, iso spin number, color spin number. And then we count how many independent of degrees, and then we ask a question. When we unify all these quantum numbers to be a single one, then we ask this particle, this single particle, in which dimension of space-time they move, their motion, okay? For the Dirac equation, just do another way. Dirac said we want to combine the special relativity, the 4-dimensional space-time, to electron, and then he determined that electron has 4 independent degrees of freedom. So now from standard model, we already know there's 48 leptons, quarks, and they have each, let me say, 4 times 64, 256 independent degree of freedom. We all put them together as a single field. And so there's so many independent degree of freedom. Then we ask how they could move in how many dimensions they could move in the space-time dimension. That means we do another way around to the Dirac equation. And eventually we found, so when you combine all this independent degree of freedom as a single field, unify all the elemental particles as one particles, and you ask how many dimension of space-time they can move. And eventually we found at least we need 19 degrees of freedom, 19 degrees of space-time dimension they can move. Okay, that means, okay, if we photo now the 19-dimensional space-time, and then we combine to the quantum mechanics, and the way we found it, there's 256 independent degrees of freedom for this single particle. So then that's ideal. So then we use the gravitational quantum field theory as a framework. So we separate the symmetry of this single particle with 256 independent degree of freedom. So they have this spin symmetry, actually. This spin symmetry, SP118. And then we know they need 19-dimensional space-time in the coordinates. So then this symmetry as in the Minkowski space-time, the super Minkowski space-time. So they have the Laurent symmetry, SO118. Then we separate these two symmetries, and we gauge this symmetry, SP118 as gauge symmetry, to introduce gauge field to describe the interactions. Okay. And then when you distinguish these two symmetries, and you have to introduce from space-time, then introduce the field with bicovariant vector field, okay? And then we have this super Pangaea symmetry and super this hyper, you can hyper Pangaea symmetry or hyper spin symmetries. Okay. And then here I didn't discuss before, so we should include some scaling symmetry. This is a local scaling symmetry, the global scaling symmetry in coordinate, local scaling symmetry. When you discuss the universe, expansion or development, so we have to know how big of a universe, then have to discuss scaling symmetry. Okay. The time is?
Yeah, thumbs up.
Yeah?
Yeah.
Okay, so then we have a few questions or discussion, or I will for the next lecture.
Okay. Okay. So let's thank Professor Wu for the very interesting talk. Any questions? Yeah.
May I ask, if you gauge the spin of particles and assume this gauge field propagates mediate gravity, then how do scalar particles couple to gravity, like Higgs boson, since they don't have spin?
The scalar particle or the bosons? Yeah, that's a good question. So you will find that for all spin 0, spin 1, the boson, all the bosons interacting with gravitational interaction, you can always use metric field because they're independent of spin. Okay, but for the spin gauge boson and for the spinors, leptons and quarks, they have spin, so they can only couple to bicovalent graphic gauge field is K mu A. So that means you can not only use metric to describe all the interactions. So then when now the metric is metric can be considered as the composite field of the graphic gauge field, the K mu A. You contract with the spin A, yeah? That means the basic gravitational interaction only be the graphic gauge field. So with K mu A, with this bicovalent factor field, because the leptons, quarks, coupled the only with this gravitational field, not coupled to the metric. Yeah.
Thank you.
More questions?
Is that normal?
What?
Is that renormalizable?
Renormalizable?
Yes.
Good question. Actually, in the paper, longer paper, like graph dynamic and spinor dynamic, electrodynamics, I got a question from referee, so then I answer a question on that paper. Because before that one, I already developed a new regularization scheme. Because we know, even in the quantum field theory, QED, QCD, there's renormalization problems, you have divergence. So usually we use the dimension regularization, okay, to regularize the well-defined divergent integral. And you can prove the theory is consistent, okay? You can absorb all the divergence to the physical observables, like couplings or mass and so on. But then the question is, in dimension regularization, you have to modify the original theory. You from 4 dimension to the 4 minus epsilon, yeah? Reduce the dimension, okay? So what happens when you do that one? You will find that when you calculate the Feynman diagram, the loop diagram integrals, and you will find if the loop has the quadratic divergence and logarithm divergence, the dimension regularization always reduce the quadratic divergence to be logarithm divergence to satisfy a consistent condition, I call it that. And so why the theory becomes renormalizable, okay? And you can absorb all divergence. But you lost the quadratic divergence. And then I saw some people want to discuss the dynamic symmetry burden. They need this, and you cannot use dimensional regularization. And then we know also the Carroll theory, the anomalies, for example, and the supersymmetry. You have exact dimension. You cannot reduce the channel dimension to the 4 minus epsilon or 6 minus epsilon and so on. You have to have exact dimension. So then people have to modify the dimension regularization to call it as modified dimension regularization to introduce something, okay? And then otherwise that become inconsistent. So for that one, so I developed a new regularization. So I calculate original theory with exact dimension, and then I redefine the divergent integral, just a simple redefine divergent integral, and then I can calculate quadratic divergence, logarithm divergence, and so on, and then I can calculate all the symmetry of the theory. Then I can introduce 2 scales. I call it characteristic scale. One scale as the ultraviolet cutoff, apply the law as the ultraviolet cutoff, and another scale apply the law as the infrared cutoff, without destroy the symmetry of the theory. That means the divergence in the quantum field theory is a mathematical divergence, and it's not a physical one. So I can always redefine this divergence integral to be well defined, okay, and then to make renormalization, okay. And then when you, especially for quantum field theory, I have to introduce two categorical energy scales, okay, by hand without the symmetries. But when in the presence of gravitational interaction, as I discussed, I have to introduce the local scaling gauge symmetry. When you have local scaling gauge symmetry, that means the theory can always have a fundamental scale. When you fix the gauge, you can always define the fundamental mass scale. So that can probably rule as the like calculated energy scales. So that means in a gravitational quantum field theories, you have a fundamental scale, and also in the gravitational quantum field theory, I believe there's no divergence because there's no infinity, not in the divergence. There's no infinity because, as I show, the gravitic gauge field, when you define the spin-related gravitic gauge spacetime, so you have always the derivative, coordinate derivative, or coordinate displacement multiplied by the gravitic gauge field. But in the quantum field theory, how the divergence come from is because you have this space-time, this global flat, and you can go to the 0 point. It's just 1 point from the uncertainty principle. When you go to the point, you have the infinity. Okay, momentum, you have infinity. So this is why string theory say when we extend it to one-dimensional string, so not go to point, so there's no divergence. Okay, so that's the advantage of distinction. But actually here in gravitational quantum theory, you notice that you don't need to do that. Because when you have the momentum operator, the partial mu, okay, to get momentum. The partial mu in the coordinate spacetime, when you have the gravitational interaction, it's always coupled to the gravitic gauge field, the K mu A hat. The hat means the inverse of gravitational field. So the derivative operate of coordinate spacetime always coupled to the inverse of gravitic gauge field. So when gravitational field, when the field goes to infinity, the inverse of gravitic gauge field goes to 0. So when you just consider the point, the high energies, all the field goes to high energies, including the gravitational field. Okay, its inverse goes to 0. So then you have always 0 times infinity, the momentum of partial mu. So that should be finite. Okay, if it's considered theory. So there's two reasons. One reason, the scaling gauge symmetry, you have fundamental scale. Second reason is momentum operator partial mu always multiplied by the inverse of gravitational field. So when the momentum goes to infinity, this field goes to 0. So then that it should be a finite number.
Okay, due to the limited time, for more questions, please ask Professor Wu in private. Okay, let's thank Professor Wu again. Okay, we're gonna take a few minute break and we prepare for the next online lecture.
So the schedule in the afternoon is as it was, and the schedule is something before.